I don't know if you watch all my videos, and if you don't, that's okay. I'm not going to judge you. But I made a video about electric fields, and I had this problem. I'm going to describe the problem to you, and I hate the problem. And I hate this problem so much that I'm going to solve it 3 times, just to show you how much I hate this problem. It's a terrible problem. I'll tell you why it's a terrible problem, and then I'll solve it 3 different ways, and then I'll make a better problem. And that's what I'm going to do. So if you don't like physics or Python or silly physics jokes, then you may not like this. But if you like those things, maybe we'll have a good time. Okay, so let me describe this problem. So I was making a program to calculate the electric field due to multiple charges, and I said, let me just look up an example in a book, and I found this problem. So we have 2 charges at the corner of a square. They both have the same magnitude charge, Q1, Q2, of 7 microcoulombs. And the length of the square is 3.3 meters. So the question was, what's the electric field at A? They also asked for B. They also asked for here. What's the electric field at A? Okay, that's an okay problem. It's not great. It's really not great, but it's okay. And then they said, well, where would you have to put a third charge such that the total electric field at A is 0? That is a bad problem. Okay, so let's just talk briefly about the physics. So the first thing is, what if I want to calculate the electric field here? If I want to find 0, I'd have to find the total electric field. So the first thing would be to calculate the electric field due to this charge at A and that charge at A. And we can use the following equation for electric field. E equals, I'll just call this K. K Q over R squared R hat. So in this expression, K is the Coulomb constant. K is 1 over 4 pi epsilon naught, which is 9 times 10 to the 9th Newton meters squared per Coulomb squared. R, if I have some random charge, I could put the charge anywhere, and I need to know the observation location. I'll call that. Let's call this RO for the observation location. We'll call this RQ for the location of the charge. Then this is R, such that R is going to be RO minus RQ. And then I can find the magnitude of that goes in here. The unit vector R hat is the vector R divided by the magnitude of R. And that's important because Q is a scalar, that's scalar. I need to turn this back into a vector. And I need to do that. I need the vector value of the electric field, because let's just draw this here. Suppose I have charge 1 right here. It's going to make an electric field like this. I'll call that E1. And charge 2 has a different R value, but it's going to make an electric field like that. And so then I want to find the total electric field due to those 2. And then, which is going to be like this. E. I call that E1 too. I'm going to show you the solution in a second. So then if I want to put a third charge, it'd have to be somewhere over here, so that would make an electric field this way, E3, and that all add up to 0. That's what we want to do. Okay, and it's such a terrible problem, I didn't want to go through and work out the whole thing, so I worked it out, which I don't normally do, but I don't want to waste your time, okay, on problems that I don't like. So let me just walk you through what I did. Q1, Q2, just like before. E1, E2, just like before. So the first question is, what's the electric field at point A due to E1 and 2? And I call this E12. It's just electric field E1 plus electric field E2. Okay, so I try to do this in as nice of a way as possible. So E1 is going to be, this is the charge of that. I know the distance is A. This is not the way I would do it. Okay, I'm trying to do it the way I think they would have us do. KQ over A squared, because its distance is A. And then I need to make it a vector. It's going to be in the y direction. So 0, 1, 0. That's my vector in the y direction. That's a unit vector. Okay, now for this charge, I need to find the distance. And so the distance, this is A, that's A. So this is going to be square root of A squared plus A squared, or square root of 2A. And I need to find that unit vector. And this is kind of like at a 45-degree angle. So you could do it a different way, but I just wrote it as the vector negative 1 over the square root of 2, 1 over the square root of 2, 0. So if you find the magnitude of this, you do get 1, right? Because this is going to be, you square this, you get 1/2. You square that, you get 1/2. Square root of 1 is 1. So now I just put it in over here. E2 is kq over the distance squared. So I square this, I get 2a squared, and then I have my unit vector right there. Then to get the total, I just add this and that, and I get kq over, that's an a, that's not a q, it's an a squared. And then I have, in the x direction, I only have this component, right? But I had to bring the 2 in so that they both have this kq over a squared I can factor out. So I have negative 1 over 2 root 2, and then I have 1 over, that should be 2. That should be 2, right? Because it's 1 over 2 root 2 plus 1. I add them together in the y direction. And then so that looks like, I tried to simplify it, and I think I made a mistake now that I'm looking at it. And so, I didn't finish. Okay, so there may be some mistakes here, and I don't really care. So then I get that's my vector, E12. Now, I need to find, if I want to find the location of the charge, it's going to be in the same direction as E12 from A, right? So I need to know that direction. So that's where I get this E12 hat. I just take this is my vector. I have to normalize that, and I divide it by the square root of that value, and that's what I get. And then I want to say E is E3 plus E12. So E3 is negative 1 over 1, is the opposite of 1, 2. But the magnitude is pretty easy. I can find that distance, right? It's going to be kq over s squared, where s is the distance along that path. I know this is a complicated problem. I told you. I said, hey, this is a bad problem. So then I can solve for s, and I get that. That's not squared. Yeah, that's not squared. And then I can find s vector. The s vector is s hat, where s hat is s e hat, E12 hat, right? That's in the same direction. So now I have it as a vector, and then I can find the location of that charge by my location of A plus that vector, and that's that. Okay. Whew. I think, did I do this? Let's see. I think I did this. Yes, I did. And I think I'm getting the right answer. But let me show you my code, because what I did, I wrote a function that calculates the electric field, and I can use it in multiple cases. Let me show you what I have in the code, and that's going to be my first solution. And then I'm going to use that code to make a better solution. Okay, so let's switch over here to the computer. Okay, let me make this bigger so that you can see it, because that's too small. Okay, let's just briefly go over this. I don't want to spend too much time on bad problems. But, I'm willing to spend time on bad problems because that's what I like to do. Okay, so this is my function, right? That's my function. I give it the location of the charge. I give it the location of the observation location and the charge, and it returns the electric field. So that's useful. Don't worry about that graph. There's my 3 charges. This is the location of charge 1 and the location of the observation location A. And then this is the location of charge 2. Yeah. And then so I calculate E1, calculate E2, calculate the sum of E1 plus E2. And then I print that. I print the magnitude of that. And then this is the unit vector in the direction of E12. So that's all in Python. Then I calculate the distance S, right? The magnitude of the distance from the point to that place. It's just going to be the square root of k q3 over the magnitude of E12. That's what I did on the paper. I can print that distance, and then the actual S is just like I said, S mag times, that's E12 hat. I know this is complicated. I know it's complicated. Note, this is the algebra. This is a problem from an algebra-based physics course, not even a calculus-based physics course. Now to find the location of RQ3, I need to take that vector from point A and add the location of point A so I can get all the actual location of that charge. I print that out. I print E3, the electric field, and then I print the total electric field right there. Let's run this and see what happens. Okay, so here's my total electric field. You can see it's practically 0, 10 to the negative 11 to 10 to the negative 10th. S is 2.253 meters from that thing, and then this is actual vector location of that, negative 0.06, 0.54. So I solved the problem. Done. And honestly, I don't know if that's the right answer. I mean, it is the right answer because I calculate. If I know the location, I can calculate the value of the electric field pretty easily using my function, and I did. Okay, I assume the way that the book wanted people to calculate that. Okay, let's do it a different way. Let me skip over here to paper, because I'm going to do it the way that I like to do it. Yeah. Okay, so skip over to paper, and I can describe what I'm doing. Okay, so here's my charges. Q1, Q2, and that's A. So the first thing I can do is to find E12. And let's just draw it like this. And I already said that if, in order for E net to be equal to E12 plus E3 equals 0 vector, then E3 has to be going this way. And that means that the R for that charge has to be along this path. So it has to be some distance S this way, which is the same thing as I had before. So I have some distance S, and I can find the vector location of that charge. RQ3 is going to be equal to RA, the location of A, plus S E12 hat. Right? E12 hat is a vector with a magnitude of S in the direction of E12. So that is true. So what I want to do is just pick a location right there. And with that, put my charge there, calculate the total electric field right here. And then I'm going to move it and do it again, and move it and do it again. So I can make a plot of the total magnitude electric field as a function of S. And when that gets to 0, that should be my answer. Does that make sense? I like that solution. Okay, so let's do that in Python. Okay. So I'm switching back to the computer. Here's my code. Oops, down here. I keep doing that. Let's just go up here. I'm just going to copy some of this stuff. All this stuff down to E12. Yep. Copy that, and let's make a new trinket. Let's make a new one. Oops, I don't know why it does that. Let's see. I don't know why. New trinket, glow script, because it's got the vectors in there. Python. Okay, paste. Okay, so there I have all my code. Let's make it bigger, bigonate. Okay, so I've calculated E12. So let's go ahead and make a graph. So I'm going to say G1 equals graph. X title is going to be equal to, let's just call it S in meters. And the Y title is going to be equal to E mag. What's this called? E total in newtons per coulomb. Let's put some other stuff in here. I'm not going to give it a total title, but let's give it a width. Otherwise, it turns out weird. 500 height equals 250. Oops. Okay, so that's just my stuff to make the graph. That just puts the axis in there. And I can say F1 equals G curve. Color equals color dot blue. I like blue the best. That's going to be the graph I actually plot. So now I need to start off with a value of S. I need to pick a value for S. Let's just pick S equals 0.1. And so, let's call it S mag. Right, I want S to be the vector. So that's the magnitude of my distance from point A. Now I need to know how big I'm going to step that. ds equals 0.001. I'm just picking stuff. If it doesn't work, don't work. Okay, and now while S mag is less than 0.3. I think it should be that. That's how far the box is. I'm going to go that far away. Then the first thing I'm going to do is say smag equals smag plus ds. Because I always forget that. If I don't increment my size, I'm going to have an infinite loop. And if your Apple, infinite loops are cool. But for Python, infinite loops are bad. Okay, so now what I'm going to do is to calculate the location of RQ3. So I'm going to calculate the S. S equals smag times norm E12. Now RQ3 is going to be RA plus S. Now I can calculate E3. E3 is going to be my function. So up here, you'll see I have my function right there. So I need to give it the location of the charge, the location of the observation location, and the charge. So this is going to be equal to E, what did I just say? The location of the charge, which is RQ3. The location, the observation location is RA, and then the charge is Q3, which is, they're all the same, but that's fine. Now I can find the total electric field, E net, is going to be equal to E12, which doesn't change, plus E3. And now I'm going to plot that. So I'm going to say F1.plot S, let's see, S. Let's just do S. No, Smag. Smag, I can't plot S, S is a vector. Smag, and then norm, no, mag, E net. Okay, do you think this is going to work? Sometimes I just kind of like put stuff out there and I don't really know what's going to work or not. So let's just run this. If it doesn't work, we'll just say it doesn't work. Probably like that. Okay, let's save this. Plot to find Q for E net. And that's a bad title, but that's fine. So you'll notice here, oops, let me run it again. You'll notice here that as I move further away, the total electric field decreases. This is the magnitude. And then right there, it gets to 0 at 0.253-ish. Okay, let's find that exact point. Let's do a little cheaty thing here. Well, not cheating, but this is kind of silly. So let's call this E net min equals. So what I want to do is to find the minimum electric field, and then for that minimum electric field, assign that value for S. So I can just print it. I don't have to get it from the graph. So in order to do that, I need to actually find E net min. So let's just do all of this before the loop too. It's kind of redundant, but. So E net min is going to be the magnitude of E net. That's whatever I start with. That's the first starting point is my minimum. And then I need, let's just call this S min, which is the S value for the minimum. And let's just call that S mag. Okay, so when I calculate E net, I'm going to say if mag E net is less than E net min, then E net min is equal to mag E net. Right? So if it's lower than the minimum, then that's the new minimum. And S min is going to be equal to S mag. So only if it's lower do I reassign the values. So with that, after my loop is over, I can say print S min equals S min. It's technically in meters. Okay, let's see if that works. There you go, 0.24. Now, maybe you want a better answer. I can get that. Let's do this. So I see here that I could start here at 0.23. So I don't have to start at 0.1. So I can start up here at 0.23. And then since I'm starting later, I can make ds smaller. And there. Now that's S. I didn't calculate the location. You can do that. I guess I should do that real quick. So edit the code. Now I know that S min. I can say, oh, I've already found it there. No, I didn't. So print RQ3 equals, it's going to be equal to RA plus S min times norm E12, and that will be in meters. And there's your location. That's the same as I got before. That was the second way to do it. The third way is kind of fun, so let's get right to it. Let me skip over here to the paper and show you what I'm going to do. I need a new piece of paper. Okay, I got more paper. So let's draw a picture on the paper. This is called a Monte Carlo calculation, and I love Monte Carlo. They're just fun. So let me start with my picture. Here's Q1, here's Q2, and here's A. Okay, so I'm pretty sure that in this region, I can put a charge somewhere in this region such that the net electric field is 0. So let's call this region, let's say this is 0.3 by 0.3. So I'm going to go 0.3 in the negative x direction, 0.3 in the positive x direction. So all I need to do is to find a vector in this area and just pick a point. I'm going to just pick a point and then calculate the total electric field here. And then I'm going to do it for another point, another point. I'm going to randomly pick points in this box until I find one that works. And you think that's dumb. It's not dumb, it's Monte Carlo. Okay, so how will we find these points? The first thing is I do have this vector RA. And then I need to find this vector to my point. And I'm going to say RQ3 equals RA plus the vector. I want to go from negative 0.3 random to 0.3 random. So random is a function in Python that returns number between 0 and 1. So this will give me an x-coordinate between 0 from here and negative 0.3 and 0 and 0.3 and 0. Okay, so all I need to do is generate a bunch of those points, and just what I'm going to do is actually draw those points as I'm going to plot dots. And if the value of the electric field is less than, let's say, 1 times 10 to the 5th, because that was around what I was getting, I'm going to make it a different color. Okay, so let's get started. So let's, again, go down here. I'm going to copy the code. Let's just copy the code. No, copy that one right there. Oh, I didn't switch over to the computer. I'm sorry. Computer. Copied the code. Okay, so let's get rid of the stuff we don't need. So this one, I'm going to leave all that there. G1 is graph. Now I'm going to plot, let's plot SX versus SY. So this is going to be S, and so it's measured from the point. So SX, SY, SY. I mean, I guess I could plot X and Y, right? Let's see what I did. I did this before. What did I do? I want to do the same thing because it worked nice. No, let's just do X and Y. X and Y. And then I don't want it to be squished. I'm actually going to do 500 by 500. Now F1, I do not want G curve. I want G dots. So the difference is that G curve connects the points. G dots does not. So I can just draw a bunch of dots. So I'm going to go down here and say G dots, and that's going to be blue. And then I need another function, F2 equals G dots, color equals color dot red. Okay. So now let's just go down here. I don't really need all that stuff. I'm just going to delete this. So let's say n equals 0, n equals 1,000. So that's going to be my counter. And there's lots of ways you can count, but I'll show you how I like to do it. While n is less than n equals n plus 1. So this will go through and count up to 1,000 or around there. It doesn't really matter. Let's just go ahead and now let's generate a random variable. So I'm going to say R temp equals RA plus vector 0.3 times random. That should be negative, right? Because I'm moving in the negative x direction. 0.3 times random, 0. So that's my random vector. And let's just plot that. I'm not going to calculate anything. I'm just going to plot it to make sure everything's working. F1.plot. Actually, let's do F2.plot. No, let's do F1. F1.plot. Rtemp.x, Rtemp.y, 0. So this will plot all my points, 1,000 points, and it should be kind of boring, but that's fine. And it's very boring if it doesn't work. Must be plot or plot data. What did I do wrong? F1.plot. Oh, sorry. I gave it 3 coordinates. It's like, I can't plot 3. Okay, so there's 1,000 points. That doesn't even look like 1,000, but that's 1,000. So we're looking pretty good. And it does go, this is in the negative x direction. Okay, so now what I want to do is to calculate the electric field at A due to each one of these. And if it's small, I'm going to make a red point instead. So let's calculate the electric field. So I can say E3 equals E of R temp, RA, Q3. And then E net equals E12 plus E3. If mag E net is less than 1 times 10 to the 5th, because remember these are big electric fields, then I'm going to plot F2. So I'm going to say F2.plot rtemp.x, rtemp.y, else plot the blue one. It should work. Let's run it. I feel like I made an error. I'm just telling you right now. I feel like there's an error. I can feel it. I can feel errors. There's not an error. Okay, check that out. That's pretty cool. Let's make this. So here's all my points. These points have a smaller electric field, right? So my location of my charge should be where it should be somewhere here. And you'll look, I have negative 0.6 times 10 to the negative 2, which is very close to what I calculated before, and 0.5. So we're really close. Let's go back over here. Let's decrease the size of my electric field barrier to 5 times 10 to the 4th, and let's see what happens. Okay, so now see I'm getting much closer, right? And if I decrease it even more, I'm probably going to get a problem. Let's do 1 times 10 to the 4th. And you see it's not there. Okay, but if I run it again and again, aha, got it. Of course, you can fix this by just having more data points. Let's run 5,000 data points. And you can't see it. Okay, I want the blue to be smaller. Let's see. So I can't remember how to do that. So let's go over here to glowscript.org. We'll change to WebVPython. I know that. Don't tell me. And I'm going to go to Help. And I'm going to go to Work with 3D Objects, Graphs, G dots, because you can choose the size or something. G dots. You can give a data point, blah, blah, blah. For G dots, you can specify as a radius or size attribute, which specifies the radius or diameter of the dot. Default size is 3. Okay, so let's do, it says radius or size. So is this the right one? Yeah. So let's say G dots 2, let's say size equals 0.5. That didn't work. No, I want to change this one to 0.5. Size equals 0.5. Yep, see? I love it. I love it. Look at that. I just want to look at this for a little bit. And now if I run it again, it might be a little bit. See, that one didn't get it. Run it again. Run it again. Okay, so that happens clearly. I just need more data. More Monte Carlo, 10,000. There you go. That's just the best. Okay, so Oh, I did tell you one more thing. I'm not done. One more thing. One more. I'm going to say, let's go back to this problem. What's wrong with this problem and what would be a better problem? Okay, so switching back to paper. I'm going to give you the code for these things if you want, so you can play around with it. Monte Carlo is awesome. If you haven't played with Monte Carlo, you should play with Monte Carlo. Okay. So let's just write down the problem and really describe why it sucks. Because yes, it does. Okay. And maybe I've written bad problems before. We've all written bad problems, but maybe someone just thought it'd be easier and didn't really check it. But this is a hard problem. So here's the problem. And there may be a trick to it, but that doesn't mean that doesn't make it a good problem. So we're trying to find the total electric field right there, and this charge is up here somewhere. Okay. So it's a bad problem because in order to get this, you can see the algebra that you have to do to get this, which doesn't mean it's a bad problem by itself, but why are you giving this problem to an algebra student? What is the goal of this problem? Normally, we would give problems to help them understand that, yes, the net electric field is the sum of the individual electric fields. But this just makes it like complicated for no reason. That's the problem. And if there's a trick to solve this, which I think there could be, maybe I missed it, and if you know what it is, you feel free to let me know. What is the goal of the course to know tricks? I don't think so. Tricks are for kids. So that makes it a bad problem. Okay, I think finding electric field there's okay. The better problem would be like finding electric field right there because there's some symmetry if you don't want to deal with unit vectors and stuff like that. But here you pretty much have to do unit vectors. Or if you use Python, it's cool. Let's pick a different problem. What about this? Q1, Q2, A, Q3. So where do I put Q3 so that E here is 0? That one's not so bad, right? Because here I can say E1 is in the x direction, E2 is in the x direction, and then how far do I get this away? And let me just go and write it out. So because it's only in the x direction, it's not too bad. Let's call this distance S, and then we can find the location. So I'm going to say E1 as a scalar. This is the x direction, actually. K, Q, they're all value Q. And then this one has a distance of 2a. So it's going to be 2a squared. It's going to be 4a squared. E2x is going to be KQ over a squared, right? Because that's the distance for that one, a. And then QE3x is going to be negative KQ over s squared, where I don't know s. But if I add these up, I have to get 0 as a scalar because it's only one dimension. So let's say KQ over 4a squared plus KQ over a squared minus KQ over s squared equals 0. Well, I can divide everything by KQ, and I get 1 over 4a squared plus 1 over a squared minus 1 over s squared equals 0. So now I can add s squared to both sides, and I can get a common denominator. This is going to be 4 over 4. So I get 5 over 4a squared equals 1 over s squared. Then I can flip both sides. S squared equals 4a squared over 5. S is going to be the square root of that. And that should give me an electric field of 0. And let's just to show you that I just made that up off the top of my head. I just went, boom, made it up. Okay, if I have the same value of A, let's find the value of S, and then put 3 charges there, and see if we get an electric field of 0. So switching back to the computer, I'm just going to use the same program. Oh, it's still... Oh, I'm on down here. I'm sorry. I do that all the time. Okay, so let's just comment out all this stuff. Now I'm going to change my values up here. I don't really want to do this. I shouldn't. Okay, let's actually do this. Uncomment. I don't want to mess up my nice program. Let's just copy it. Save. And then copy it again, copy of a copy. Okay, so now I can just delete stuff and I'm not afraid. I have so many programs over here, it's just sad. Now I'm going to say RQ1 is the same place, RQ2 is the same place, but RA is now, I said it's on the x-axis, so it's 2 times 0.30. So E1 is the same, E2 is the same, and then I can calculate S. I'm just going to use my equation. S equals square root of 4 times 0.3 squared divided by 5. And then I need to find the location of 3. RQ3 is going to be equal to vector 2 times 0.3 plus S 0, 0, right? Because it was 2A and then I had an extra S. And now I can say E3 is going to be E, and it's going to be RQ3, RA, Q3. And then print, let's say ENet. ENet equals E1 plus E12. And that E12 did change too. And then print ENet equals ENet newtons per coulomb. And it should be close to 0. It's not. What did I do wrong? So RQ1's at 0. I put, that's RA is 2. R3 is 0.3. E, that's still the same. That's still the same. S is, oh, you know what? Is this a problem? No? Huh. Okay, S is equal to the square root of 4a squared, square root of 4a squared divided by 5. And then RQ3 is 2 times 0.3 plus S. Okay, well, I'm not gonna waste your time. I did a mistake that I ended up in the last video. I still think it's basically the right solution, but I don't really care. I really wanted to show you that other problem is bad. Okay, so like I said, all the links to the codes will be down below. Hope you had fun. It's a bad problem. Don't make bad problems. I'll talk to you later.